Yes. Hello everyone, welcome to MK Academic Solutions. So in this video, I am going to explain you about the chemical equilibrium. Following the topics are going to be covered in this video. So what are the topics I am going to cover in this video? That is units of Kc and Kp, relation between Kc and Kp, factors influencing on equilibrium constant, and applications of equilibrium constant. Okay, now let us start our video without any wasting of time. So the first topic is what? Relation between units of Kc and Kp. Okay, units of Kc and Kp. We know what is Kc and Kp. It is the ratio of rate constant of forward reaction to rate constant of backward reaction, or it is the product of concentration of products raised to their stoichiometric coefficient by product of concentration of reactants raised to their power stoichiometric coefficients. Okay. So now let us take one hypothetical equation to derive the units of Kc and Kp. Okay. So now here I am going to take an hypothetical equation. A moles of A plus B moles of B is gives rise to C moles of C plus D moles of D. This is the hypothetical reaction. So for this hypothetical reaction, let us express the Kc. So here Kc is equal to concentration of products, concentration of C power C, concentration of D power D by concentration of A power A into concentration of B power B. This is the expression of Kc. Now here, what is the units of concentration? What is the units of concentration? Here generally we will take moles per liter. Okay. So this is moles per liter power C. So concentration in units of C I am going to take here, and next concentration of D is also moles per liter power D by concentration of A also moles per liter power A into moles per liter power B. Okay, these are the units of different reactants and products. Now here mole same, if bases are same, powers must be added. So therefore moles per liter power C plus D by, here denominator also moles per liter power A plus B. Okay. Now see here both bases are same, but they are in the ratio, means here powers must be subtracted. So Kc, we will get Kc is equal to moles per liter to the power C plus D minus A plus B. Okay, this is the general units of Kc. Okay, now here Kc is equal to moles per liter to the power delta N. Okay, can I write here delta N? So here what is delta N? Delta N is equal to, so here what is C plus D? C plus D is the stoichiometric coefficients of products. A plus B is what? Stoichiometric coefficients of reactant. So here delta N I can write as number of moles of reactant, number of moles of products, minus number of moles of reactants, number of moles of reactants. Okay. So this is the what Kc, units of Kc. Now here Kp, next Kp. So in place of moles per liter or molar concentration, when you write the equilibrium constant with partial pressure units we are going to take. So pressure units generally will take atmosphere. So here atmosphere to the power delta n. Okay, simply we can take. So in the same manner we are going to substitute the partial pressure of C, partial pressure of D, partial pressure of A and partial pressure of B. So finally we will get what? Partial pressure units we are going to take as the atmosphere. So means in place of moles per liter, just we are going to take the unit of pressure, that is atmosphere we are going to take here. Kp is equal to atmosphere to the power delta n. Okay. So here in case of Kp, what is the delta n? Delta n is equal to number of moles of gaseous products minus number of moles of gaseous reactants. Number of moles of gaseous products minus number of moles of gaseous reactants. Number of moles of gaseous reactants. Okay. Number of moles of gaseous reactants. Okay. So this is about units of Kc and Kp. So now let us take the different type of examples and try to write the units of Kc and Kp. Okay. So this you understand, I just took the what? A general equation and a hypothetical equation. For that I have written the equilibrium constant expression Kc. From that Kc slowly we derived the units of Kc and Kp. Okay. Next let us see some examples. Okay. For example, 2NH3 gives rise to N2 plus 3H2. 2NH3 gives rise to N2 plus 3H2. So now here what is the units of Kc? So here Kc units are what? Moles per liter to the power delta n. So here what is delta n? We know delta n is equal to, what is delta n is equal to, children? Number of moles of products minus number of moles of reactants. Means we need to count the number of moles of products first, then after we need to count the number of moles of reactants. So we need to subtract the number of moles of reactants from the number of moles of products. Okay. So here number of moles of products, here nothing is there, means 1 plus 3 4. So 4 minus 2, that is equal to 2. So here delta n is equal to 2. So therefore units of Kc is equal to moles per liter square. So or else we just write as the mole square liter power minus 2. Like that we can write. Okay. Next Kp units. What are the Kp units here? Here Kp is equal to atmosphere to the power delta n. Atmosphere to the power delta n we are going to take. So here what is the delta n value? 2. Therefore atmosphere square. Okay. These are the units of this reaction. Next let us take one more reaction. H2 plus I2 gives rise to 2Hi. H2 plus I2 gives rise to 2Hi. So now here what are the units of Kc? So here Kc is equal to moles per liter to the power delta n. So here what is the delta n value? Delta n is equal to, So number of moles of gaseous products minus, number of moles of products minus number of moles of reactants. So here 2, only 2 is there, and here 1 and 1 minus 2, that equal to 0. Okay. So therefore here delta n equal to 0, therefore Kc moles per liter to the power 0, moles per liter to the power 0. So here we are already know anything power 0 is equal to 1. Therefore here Kc is equal to 1, means Kc does not have any units. So no units for Kc, and Kp also in the same manner, Kp atmosphere to the power 0, means here also Kp is equal to 1. So here also no units. Next, let us take one more example. Two SO2 plus O2 gives rise to 2SO3. So this is the contact process of preparation of sulfur trioxide. So now here what are the units of Kc? What are the units of Kc here? Kc is equal to moles per liter to the power delta n. So here what is the delta n value? It is the delta n value. So delta n is equal to number of moles of products, how many? 2. Number of moles of reactants, 1 and 2, total 3, minus 3. So here minus 1. Okay. So now here what is the units of Kc? Kc is equal to moles per liter to the power minus 1, means here Kc is equal to moles power 1 liter power, moles power minus 1 liter power 1, and Kp. What are the units of Kp? Simply atmosphere to the power delta n. Atmosphere to the power delta n we are going to take. Okay. Means here delta n value is minus 1, atmosphere to the power minus 1. So these are the units of Kc and Kp. Different conditions, here delta n is positive, delta n is 0. If delta n is 0, so this is very important condition. If delta n is equal to 0, there is no units of Kc and Kp. If delta n is equal to 0, no units for Kc and Kp. Okay, right children. So this is about units. Let us take one different example here. CaCO3, it is in the solid state. Upon heating, it produces calcium oxide plus CO2 gas. So now here, what is the units of Kc? So units of Kc you write as moles per liter to the power delta n. See here, what is the delta n value? Simply some people you count the delta n is equal to, so here how many number of moles of products are there? 1 mole. Okay, 1, and here plus 1, total 2, 1 here, 1 is total 2 minus here how many moles of reactants are there? 1. Okay. So here if delta n is equal to 1, okay, and here Kc is equal to okay, right. Yes, the people will write like this. Simply they will forget about the concepts what we taught previously. Simply okay, number of moles of products is 1 plus 1 2, and here number of moles of reactants is 1. So 2 minus 1 they will write like this, but this is absolutely wrong. Why delta n value if you are not supposed to take like this means here CaO is solid, CaCO3 is also solid. So what is the molar concentration of solid? Molar concentration of solid is unity 1 we are going to take. That's why if any solid and pure liquid are present in the reversible reaction or they are in the equilibrium also, we are not at all going to take their molar concentrations. We are supposed to take only aqueous and gases, not for the pure solids and pure liquids. Pure liquids and solids are having molar concentration 1. That's why we are not supposed to take. So here, however, delta n is equal to 1. Is there any other things we need to take? No. So simply here you need to take 1. But in this also you will get 2 minus 1, but this process is wrong. Okay. So if you take different type of examples, so you may not get like this. Okay. So now here delta n is equal to 1. Therefore, Kc is equal to so moles per liter to the power 1 or simply moles per liter, and Kp is equal to atmosphere to the power 1. These are the units of Kc. So now let us take one more example. NH4Cl, ammonium chloride, decomposition of ammonium chloride you take. So let us consider it is present in the solid state, okay, and it is decomposing as NH3 gas plus HCl gas. Okay. So now you see here, okay, how you will get the equation. So here delta n is equal to what? Now only I told you. So number of moles of gaseous products or number of moles of products present in aqueous state. Okay. So now here 1 and here 1 plus 1. Okay, this is the number of moles of reactants, and here number of moles, so number of moles of product this and number of moles of reactant. So we should consider NH4Cl or we should not consider NH4Cl means we should not consider the NH4Cl. Why we should not consider NH4Cl? Because it is present in solid state. So when the reactants are products in the solid state, you no need to consider the calculation of delta n and also while writing the Kc also. Okay. So here what is the delta n value? Here minus 0, nothing is there, therefore delta n is equal to 2 we will get, right? Yes. So now here Kc, so for this type of reactions you will learn how to write the Kc also. Here NH3 gas power 1 and HCl gas power 1, this much only. Here denominator you no need to take the ammonium chloride also. Even if you take ammonium chloride also, NH4Cl in the solid state we are going to take means. So here what is the molar concentration? Here it will become unity. So here Kc is equal to NH3 gas power 1 and HCl gas power 1 by 1. So that's why here what is the delta n value? You will get 1 plus 1 2 only you will get. Okay, right. So now units of Kc units are what? Units of Kc is equal to moles per liter whole square or moles square liter power minus 2, and Kp units are what? Kp is equal to atmosphere to the atmosphere square. Okay, this is about what? Units of Kc and Kp. Okay, next we will see the relation between Kc and Kp. So now what is the relation between the Kc and Kp? Okay, let's see relation between Kc and Kp. So now let us take the hypothetical reaction. A moles of A plus B moles of B is gives rise to C moles of C plus D moles of D. Okay, this is the hypothetical reaction. For this hypothetical reaction, we express the Kp. So here what is Kp is equal to, first let us write the Kc. Okay, first we write the Kc. So what is the Kc is equal to here? Kc is equal to number of moles of gaseous products. Sorry, Kc is equal to what? It is the product of concentration terms of products raised to their power stoichiometric coefficients by product of concentration of reactants raised to their power stoichiometric coefficients. Okay, so simply concentration of C to the power C and concentration of D to the power D by concentration of A to the power A and concentration of B to the power B. Okay, this is the Kc. Now here Kp. So here what is the Kp is equal to? Kp is equal to partial pressure of C to the power C into partial pressure of D to the power D by partial pressure of A to the power A into partial pressure of B to the power B. Okay, so now this is the expression of Kc and Kp. So now from ideal gas equation, so this is from ideal gas equation, what we will write from ideal gas equation? From ideal gas equation we will write PV is equal to nRT. PV equal to nRT. Therefore, P is equal to nRT by V. Therefore, here P is equal to, here N by V will become concentration. N by V will become what? Concentration into RT. Okay. So, for example, partial pressure of A, if I take partial pressure of A, concentration of A into RT. Partial pressure of B, if I take concentration of B into RT. If I take partial pressure of C, it will become concentration of C into RT. If I take partial pressure of D, it will become concentration of D into RT. Okay. So this relation we can derive from the ideal gas equations. Okay. So now here, now let us substitute the partial pressure terms in the Kp. So now we know Kp. So here Kp we know, right? What is the Kp here? Kp is equal to partial pressure of C. What is the partial pressure of C? What is the partial pressure of C? Concentration of C into RT. Okay, concentration of C. Okay, first, okay, right. Concentration of C into RT whole to the power C. Next, D, partial pressure of D. What is the partial pressure of D? Concentration of D into RT whole to the power D by partial pressure of A. What is the partial pressure of A? Concentration of A into RT to the power A, RT to the power A. Next, concentration of partial pressure of B. What is the partial pressure of B here? So, partial pressure of B is the concentration of B into RT to the power B. Okay. This is the expression of Kp by taking the concentrations instead of partial pressures. When you take the concentrations, we need to express like this. Okay. Simply what we are doing, we are substituting the partial pressures. by using the ideal gas relations. Okay. So now what you will get here. Okay, so now here only we will see. So now this equation I can write as Kp is equal to, this equation can I write as Kp is equal to concentration of C to the power C into concentration of D to the power D into, here RT is there, RT to the power C plus D. Okay, RT to the power C plus D can I write. Simply here concentration of C to the power C I separated, concentration of D to the power D I separated into RT to the power C and RT to the power C, RT to the power C into RT to the power C. So if bases are same means powers must be added. So RT to the power C plus D by, in the same manner, concentration of A to the power A into concentration of B to the power B by RT to the power A plus B. Okay, like that I can write. Now here when you observe this Kp, so what is this total term? Concentration of C to the power C, concentration of D to the power D by concentration of A to the power A, concentration of B to the power B. This total term can I write as Kc. Therefore Kp is equal to Kc into, here RT by RT. Here bases are same but they are in the ratio, so that powers must be subtracted. So therefore RT to the power C plus D minus A plus B. Okay. So now here Kp is equal to Kc into RT to the power delta n. Can I write here? So here what is the delta n here? Delta n is equal to number of moles of gaseous products minus number of moles of gaseous reactants. So here what is NGP means number of moles of gaseous products minus number of moles of gaseous reactants. Okay. So now this is the relation between the Kc and Kp. So here what is the relation between Kc and Kp? Kp is equal to Kc into RT to the power delta n. So this is the relation between Kc and Kp. Okay. Next, let us see some examples, different cases which relates the Kc and Kp. Okay. So now let us take some examples. Case 1. So here first of all, what is the relation between Kc and Kp? Kp is equal to Kc into RT to the power delta n. So now here case 1 I am going to discuss here. If delta n is equal to 0, if delta n equal to 0, what will happen children if delta n equal to 0 means? Therefore Kp is equal to Kc into RT to the power, see here, you keep a bracket here, here also keep a bracket. Why? Because some people may think only T power delta n. Okay, right. So RT to the power RT whole to the power 0. So we know anything power 0 is equal to 1. Therefore Kp is equal to Kc. Kp equal to Kc. So this is the relation between Kp and Kc when delta n is equal to 0. Means if delta n equal to 0, Kp is equal to Kc. So now let us see example. For example, H2 plus I2. H2 plus I2 is gives rise to 2Hi. So all are in the gaseous state only. H2 gas, I2 gas plus 2Hi gas. So here what is the relation? What is the delta n value here? Delta n is equal to 0. In this case 1 and 1 mole and here 2 moles. 2 minus 2, that will become equal to 0. Therefore, here there is no difference between the Kc and Kp. Next to case 2. Case 2 you see. So, here what is the case 2? If delta n is greater than 0 or delta n is equal to positive. If delta n is greater than 0 or delta n is equal to positive. Delta n. So, delta n is equal to positive. Greater than 0 is nothing but what? Positive only. Na? So, therefore, here Kp is equal to Kc into RT to the power delta n. So, here what is delta n? Delta n is a positive value. Means here what we need to do? We need to multiply with something with Kc to equalize Kp. So, now just you can imagine it as 4 is equal to 2 into 2, like that you can assume. So, now this is the Kp and this is the Kc, and here we are multiplying with the some another substance. So, that Kc will become equal to Kc. So, now here what is the relation between Kc and Kp? Here Kp is greater than Kc. Simply we can understand from this relation. Okay. Simply just for example I am telling here. So, here Kp is equal to Kc into Rt to the power delta n. So, means to equalize Kp and Kc, we are multiplying Kc with some another substance. Means Kp is always greater than what? Kc when delta n is equal to positive. See here example. Example you can take as N2 plus 3H2. N2 plus 3H2 is gives rise to 2NH3. N2 plus 3H2 is gives rise to, so okay. So, just inverse this reaction. 2NH3. 2NH3 is gives rise to N2 plus 3H2. N2 plus 3H2. Okay. So, here what is the delta n value? Here you will get 3 plus 1 4, 4 minus 1, sorry 4 minus 2 2. So, here delta n is equal to 4 minus 2, that is equal to 2. 4 minus 2, that equal to 2. Okay. So, therefore here Kp is equal to Kc into Rt whole square. Okay. So, this is the relation between Kp and Kc if delta n is equal to positive. Next, let us take the third case, that is case 3. Case 3. So, here in case 3 delta n is equal to less than 0 or delta n is equal to negative. Delta n is less than 0 or delta n is equal to negative. Less than 0 is nothing but negative only. Means sometime in exams they may give this condition or this condition. That is why we need to learn both the conditions. Delta n is less than 0 means it is negative itself. Okay. So, now here Kp is equal to Kc into Rt to the power minus delta n. Minus delta n you will get. So, now how we can relate this one now? How we can relate? So, here we can write it as Kp is equal to Kc by Rt to the power delta n. So, now how we can visualize this? How we can visualize this? So, here 4 is equal to 8 by 2. 4 is equal to 8 by 2 means you may consider it as the Kp, this you can consider as Kc, this is the Rt like that. Rt like that. Just for example only I am telling to understand the relation between Kp and Kc. Therefore, here Kp is less than Kc. Here Kp is less than Kc. Okay. So, now what is the example here? You can take 2SO2 plus O2 is gives rise to 2SO3. So here delta n is equal to 2 minus 3, that is equal to minus 1. 2 minus 3, that is equal to minus 1. Therefore Kp is equal to Kc into RT to the power minus 1, or else simply Kp is equal to Kc by RT to the power minus 1. Okay. So this is about what? Relation between Kp and Kc and the units of Kc. Okay. Next, okay, so this is the relation how we have derived.